All right, let's dive in. Today, we're going to pull back the curtain on the hidden genius that makes our wireless world actually work. We're going to explore how our networks went from being just simple, dumb pipes to these incredibly intelligent systems that manage one of the most precious resources we have, the radio spectrum.
I mean, think about it for a second. You're at a huge concert, a packed stadium, or even just a crowded city street. There are thousands of phones all around you, all screaming for data at the exact same time. So how on earth can you still post that photo or send a quick message? Well, it's not magic. It's actually some seriously clever engineering designed to solve one massive digital traffic jam.
And this digital traffic jam, it's got a name: spectrum scarcity. See, the radio frequency spectrum, that invisible highway that all our wireless data travels on, it's a finite resource. There's only so much of it. And yet, our demand for data, thanks to everything from 5G to the Internet of Things, is just exploding. And that fundamental conflict right there is one of the biggest challenges in modern communications.
Now, the old way of dealing with this was, honestly, incredibly inefficient. Regulators would hand out these exclusive licenses for huge chunks of the spectrum. Imagine giving one person their own private exclusive lane on a highway 24/7. The problem? Well, studies showed that huge parts of this licensed spectrum were just sitting there, totally unused, while other lanes were completely gridlocked. Yeah, that system just wasn't going to cut it.
So you know what happened. Engineers had to come up with something better, a smarter digital highway. And that brings us to this absolute game changer of a technology that powers pretty much all modern 4G and 5G networks, creating a system that is just way more efficient. Okay, so this slide just lays it all out perfectly. Over on the left, you've got the old way, FDMA. Each person gets one big fixed lane. So if you're just sending a tiny text message, most of that huge lane is completely wasted. But now, look at the right side, OFDMA. Instead of that one big lane, it's like we took a hammer and shattered the highway into thousands of tiny little subcarriers. This is the key. OFDMA makes the spectrum reconfigurable in real time. The network can now dynamically bundle these little lanes together and assign them based on exactly what you need millisecond by millisecond. It's the difference between a rigid, wasteful system and one that's flexible and hyper-efficient.
But all this flexibility, it needs a brain, right? I mean, if you're going to be redrawing the entire highway every millisecond, you need a traffic controller that's seeing everything and making split-second decisions. And that's where radio resource management, or RRM, comes in. And it all happens because of a constant conversation between two really critical layers of the network.
The whole thing really comes down to a simple two-step dance. First, you've got the physical layer, or PHY. Think of it as the network's eyes and ears. It's constantly sensing the signal quality for every single person connected to it, gathering something called channel state information, or CSI. Then it sends that info up to the medium access control layer, the MAC. The MAC is the brain of the operation. It looks at all that CSI data and decides, okay, how are we going to assign all those tiny OFDMA subcarriers? If your signal is crystal clear, the MAC might give you more resources to send data faster. If your signal is weak, it'll adjust. Without that constant back and forth, the network is basically flying blind.
Okay, so this is where it gets really cool. This same intelligence that lets the network sense and adapt, it also unlocks the solution to its oldest problem. For decades, the big bad wolf of wireless was interference. You know, this signal from one cell tower messing with a signal from another. But what if? What if we could flip that entire idea on its head? What if the problem could actually be the solution?
And this, right here, is one of the most brilliant shifts in thinking in all of modern engineering, taking the very thing that used to kill network capacity, interference, and turning it into a tool to actually expand it. The technology that makes this possible is called coordinated multipoint, or COMP for short. So instead of cell towers near you fighting each other and creating a mess of interference, COMP gets them to work together. They coordinate their transmissions. They can all talk to your phone at the exact same time, not to create noise, but to create one super strong, crystal clear signal. They literally turn destructive interference into a constructive, useful resource.
And this stuff gets seriously sophisticated. We're talking about techniques like interference alignment, which is kind of like mathematically shoving all the bad noise into a tiny corner of the signal where you can just ignore it. Or even crazier, zero forcing, where the network actually transmits a counter signal that is designed to perfectly cancel out interference before it even gets to your phone. It's literally an active, intelligent war on noise.
So the system is already incredibly smart, right? But the next big leap, well, it's about moving beyond a fixed set of rules and letting the network learn for itself. And that, of course, is where AI and machine learning come in. So instead of just blindly following a fixed rule book, these new networks can actually sense what's happening, learn from traffic patterns, and make smart predictive decisions all in real time. And believe me, the results are just staggering. This is data from a simulation comparing an old school static system with one that uses a machine learning model called Q-learning. Just look at the numbers here. Spectrum utilization, how well we're using that invisible highway, it skyrockets from 64% all the way up to 87%. Access latency, how long you have to wait for a connection, gets more than cut in half, from 42 milliseconds down to 19. And the fairness index, which makes sure no one user gets left in the dust, gets way closer to a perfect score. And if we just zoom in on that one key metric, spectrum utilization, that's a massive 23-point jump when you switch to an AI-driven system. That's a game-changing improvement in how we use our most limited resource. And that's all done with smarter software. No new towers, no new hardware, just brains. So let's bring it all together. What does this actually mean for you and me? Where is all of this tech heading? Well, it's pretty clear that the future of our wireless world is intelligent, adaptive, and more autonomous.
All right, let's just quickly recap the big ideas we've covered. First, our networks aren't just dumb pipes anymore. They are truly intelligent systems. We saw how OFDMA gives them that incredible flexibility to manage resources on the fly. We talked about how that link between the PHY and MAC layers acts as the network's nervous system, letting it sense and react. And maybe the biggest idea of all, interference is no longer just the enemy, it's a resource we can actually use. And finally, AI and machine learning are just turbocharging the efficiency of the whole system.
And make no mistake, this isn't some far-off future tech. This is the bedrock, the engine that powers 5G today. It's what's going to connect billions of Internet of Things devices, and it really is what underpins the future of instant, reliable communication for every single person on the planet. So, this whole journey, from dumb pipes to intelligent networks, it leaves us with one last, kind of mind-blowing question. We've built networks that can sense, that can react, that can learn. As they get more and more autonomous, making decisions way too fast and complex for any human to follow, what happens when they truly start to think for themselves? Something to think about, right? Because that future is coming way faster than you might think.